Two ancient pyramids stand worlds apart yet whisper the same architectural secrets. This video reveals the shared scientific knowledge that connected pyramid builders across continents, forcing us to rewrite history. You will discover how civilizations separated by oceans and millennia used identical mathematical constants and celestial alignments in their constructions. How could the same complex geometry appear in Egypt and the Americas without any known contact? What hidden network of ancient engineers was sharing this advanced technology? Are we ready to accept that our history books have missed a crucial global connection? From the deserts of Egypt to the jungles of Guatemala, and even in the plains of China, the pyramid rises as a silent sentinel of the ancient world. This is not a story of one civilization, but of many, all reaching for the sky with the same fundamental shape. Cultures separated by vast oceans and thousands of years, with no known trade routes or shared languages, all invested their greatest resources and finest minds into constructing these monumental triangular forms. The commonalities are impossible to ignore. A four-sided base, often perfectly square, aligned with startling precision to the cardinal directions. A towering height that dominates the landscape, built on a scale that challenges our understanding of ancient engineering. Why would this specific geometric form become the universal architectural language for humanity's most sacred and significant sites? Was it purely for structural stability, a shape that naturally resists the pull of gravity for millennia? Or was it something deeper, a spiritual symbol representing a mountain reaching up to the heavens or the descending rays of the sun? The sheer persistence of the pyramid form across isolated continents presents us with one of history's greatest riddles. It forces us to ask whether this was a case of incredible parallel development, where different minds independently arrived at the same perfect solution, or if it hints at a thread of common knowledge, a lost science that once connected our world. To understand the true mystery, we must look closer beyond the shape itself and into the precise numbers that brought it to life. The shape itself is only the beginning of this architectural puzzle. When researchers began measuring these structures with modern precision, they uncovered mathematical codes embedded in stone. The Great Pyramid of Giza holds a secret in its very proportions. Its original height, when multiplied by 2 pi, gives you its perimeter. This is not a rough estimate, but a relationship built into the core design, a deliberate incorporation of the mathematical constant pi over 4,000 years ago. This number, representing the ratio of a circle's circumference to its diameter, should not appear in a structure built millennia before it was supposedly formalized in ancient Greece. Yet there it is, a fundamental truth of geometry encoded in a square-based pyramid. This discovery echoes across the ocean. In the temples of ancient Mesoamerica, another constant emerges. The golden ratio, often represented by the Greek letter phi, appears repeatedly in pyramids like the Temple of Kukulkan at Chichen Itza. This ratio, approximately 1.618, is found in the proportions of its terraces and stairways. It is a number celebrated for its unique properties, creating a rectangle that is aesthetically pleasing to the human eye, a pattern that recurs throughout nature in the spirals of shells and the arrangement of leaves. How did builders separated by an entire ocean and thousands of years both understand and utilize these advanced, irrational numbers? These are not simple concepts like counting or addition. They are abstract constants requiring a deep, intuitive grasp of geometry and spatial relationships. The use of pi in Giza suggests the pyramid was not just a tomb, but a mathematical model of a hemisphere, a representation of the northern hemisphere in scale. The use of the golden ratio in Mesoamerica points to a desire to build structures that resonated with the harmonic patterns of the natural world. The methods for transmitting this knowledge remain one of history's greatest enigmas. Did a shared ancestral science exist, carried by forgotten migrations across now submerged land bridges? Or did these cultures develop their understanding independently, tapping into a universal mathematical language that underpins our reality? The stones are speaking a language of numbers, and the message is unmistakably the same. These precise mathematical ratios find their ultimate purpose when aimed at the stars. At the ancient city of Chichen Itza during the spring and autumn equinox, a remarkable phenomenon occurs. As the sun sets, the stepped corners of the pyramid cast a series of triangular shadows down the northern staircase, creating the undulating body of a giant serpent that appears to slither down to join its stone head at the base. This event, witnessed by thousands each year, was no accident of design. It is a perfect alignment of architecture with the solar calendar, a feat requiring generations of meticulous astronomical observation. This same obsession with celestial mechanics is etched into the very foundations of the Egyptian pyramids at Giza. The three main pyramids are arranged on the desert plateau in a pattern that mirrors the three stars of Orion's belt, with the Nile River mirroring the celestial Milky Way. This correlation is not a vague resemblance but a precise, scaled map of the heavens, oriented to capture a specific moment in the cosmic cycle. The builders were not merely stargazers, they were master cartographers of the sky, encoding their understanding of precession, the slow wobble of the Earth's axis, into the permanence of stone. This pattern of celestial alignment is a global thread. In ancient China, pyramids like those near Xi'an are aligned with cardinal points with such accuracy that it suggests a deep knowledge of polar star observation. Across the Americas, from the Sun Temple at Teotihuacan to the complex at Carol, structures are oriented to mark the solstices and the movements of Venus, a planet of great significance to many ancient cultures. These consistent alignments reveal a shared, sophisticated calendrical system. They were not just building monuments, they were constructing massive stone calendars and astronomical observatories to track time, predict seasons for agriculture, and synchronize human activity with the rhythms of the cosmos. The cosmological belief that the earthly realm was a reflection of the celestial one appears to have been a universal concept. This points to a profound conclusion that these pyramid-building cultures, separated by continents, were all participating in a silent, global conversation about the nature of the universe, using the common language of mathematics and the shared text of the night sky. The placement of these monuments reveals a geographical puzzle just as profound as their astronomical alignments. The Great Pyramid of Giza sits at the exact center of the world's landmass, a point calculated from the intersection of the longest land meridian and the longest land parallel. This is not a random coordinate, but the precise geographical heart of the Earth's continents. Such a feat implies a knowledge of global geography that seems impossible for its time, a comprehensive mapping of the entire planet long before the age of exploration. This pattern of intentional, strategic placement repeats across the globe. In Mesopotamia, the great ziggurats were consistently built on raised, stable ground near the vital waters of the Tigris and Euphrates rivers, positioning them at the center of agricultural and trade networks. In the Americas, the pyramid complex at Teotihuacan was constructed along a precise north-south axis, with its Avenue of the Dead aligned to a mountain peak that held deep spiritual significance. The builders were not merely claiming a convenient plot of land, they were selecting sites based on a complex web of factors. Geological stability was paramount, with many pyramids erected on massive bedrock platforms to support their immense weight for millennia. Access to vital resources, particularly fresh water, was another critical consideration, ensuring the survival of the large populations required for construction. But the choices often go beyond the practical. Many of these sacred sites are located in areas with unique geological features or subtle energy anomalies, places where the Earth's magnetic field or natural radiation readings differ from the surrounding terrain. Were these locations chosen because they were believed to be points of connection between the earthly and the spiritual realms, places where the veil was thinner? The consistent logic behind site selection, from the river valleys of Egypt to the highlands of Peru, suggests a shared, sophisticated understanding of geomancy, the art of harmonizing human structures with the natural and energetic landscape. This global network of precisely positioned pyramids forces us to reconsider the scope of ancient exploration. It paints a picture of a world far more interconnected, or of cultures with a far deeper, more intuitive knowledge of the planet they called home. The stones themselves hold another layer of the mystery. Deep within the quarries of Aswan, Egypt, workers carved multi-ton blocks of granite, one of the hardest stones on Earth, with a precision that defies simple tools. They used not brute force, but a sophisticated understanding of material properties. Diorite pounding stones were employed to pulverize the granite along a desired line, and wooden wedges, soaked with water to expand with immense force, would cleanly split the rock. This was not guesswork, it was applied material science. An ocean away, Mesoamerican builders worked with volcanic stone, another challenging material. At Teotihuacan, they used obsidian tools and water-based abrasives to shape and polish the tough basalt and andesite, achieving seamless joints without a drop of modern mortar. This shared knowledge of how to manipulate different stones speaks to a deep, practical engineering intelligence. The transportation of these colossal blocks reveals another universal challenge met with similar ingenuity. The Egyptians are believed to have used sledges lubricated with water or another substance to move stones across the desert, a method depicted in tomb paintings. In the Americas, evidence suggests the use of log rollers and enormous manpower to transport stones from distant quarries through dense jungle terrain. The solutions, while adapted to local environments, demonstrate a common grasp of physics and logistics. Perhaps most telling is the mortar that binds these structures. The Romans would later perfect concrete, but ancient pyramid builders developed their own complex, geopolymer-like compounds. In Egypt, analysis of the mortar in the Great Pyramid shows it is stronger and more durable than the actual limestone blocks it holds together. At the Bolivian site of Pumapunku, stones are fitted with such precise, interlocking joints that not even a razor blade can slide between them, a testament to an advanced knowledge of material tolerances and composite construction. When we compare the lifespan of these ancient monuments to that of many modern buildings, the results are humbling. Our contemporary structures, often built with steel that rusts and concrete that cracks, are designed for a lifespan of decades, maybe a century. The pyramids were built for millennia to withstand earthquakes, erosion, and the relentless passage of time. This consistent, global application of durable material science and sophisticated construction techniques points to more than independent trial and error. It suggests a shared, hard-won body of practical knowledge about how to build for eternity, a legacy of engineering genius that we are still struggling to fully comprehend. Step inside the king's chamber of the Great Pyramid and speak in a whisper. Your voice will not fade, but will travel with impossible clarity to the farthest corner of the room, audible to anyone standing there. This is not a quirk of empty space, it is a carefully engineered acoustic phenomenon. The entire chamber functions as a giant resonant cavity, its dimensions and the specific granite used in its construction tuned to amplify and carry sound waves in a way that defies normal acoustics. This mastery of sound is a global signature. At the Mayan site of Chichen Itza, stand before the Great Pyramid of Kukulkan and clap your hands once. The echo that returns is not a simple repetition, but the distinct chirp of the sacred Quetzal bird, a sonic effect precisely calculated by the pyramid's towering staircase. Across cultures, these builders were not just shaping stone, they were shaping sound itself, designing spaces that could transform a whisper into a proclamation or a handclap into a divine symbol. The stones they chose contribute to the mystery. Granite, widely used in Egyptian chambers and in structures across the Americas, contains quartz crystals. When subjected to pressure or vibration, quartz generates a small electrical charge, a property known as piezoelectricity. The very stones of the pyramid, compressed under their own immense weight and energized by the seismic hum of the earth or even by sound vibrations, could have been producing subtle, measurable energy. This leads to a startling question. Were these structures designed not just as tombs or temples, but as sophisticated energy devices? Modern researchers have documented unusual electromagnetic fluctuations within certain pyramid chambers, with compasses behaving erratically and instruments detecting energy spikes. The pyramid shape itself, when studied in scale models, appears to concentrate electromagnetic energy into its internal chambers and base. It seems these ancient architects understood principles of resonance and energy that our science is only now beginning to measure. They built devices of stone that could interact with the planet's own frequencies, creating spaces where sound and energy behaved in extraordinary ways. This shared, advanced knowledge of physics suggests a lost chapter in human history, one where the line between architecture and advanced technology was profoundly blurred. Beneath the dry sands of Giza, a hidden network of channels tells a story far older than the pyramids themselves. Recent surveys have revealed intricate waterways carved deep into the limestone bedrock, a sophisticated plumbing system designed to control the groundwater that threatened the stability of the massive structures above. This was not a simple drainage ditch, but a carefully engineered solution to a complex geological problem. Half a world away, at the jungle temple of Angkor Wat in Cambodia, a similar system emerges. Vast moats and reservoirs, known as barrays, surrounded the temple complexes, functioning as massive hydraulic engines that regulated water levels and prevented the stone foundations from being undermined during the monsoon floods. The parallels continue in Mesoamerica. At the ancient city of Teotihuacan in Mexico, beneath the Avenue of the Dead, archaeologists found a web of underground conduits that channeled water from nearby springs, directing its flow with a precision that rivals modern civil engineering. The practical need is clear. Water is a destructive force that can erode the strongest foundations, but the purpose of these systems ran much deeper than mere utility. In Egypt, water channels were integral to the pyramid's symbolic journey, representing the primordial waters of creation from which the mound of life emerged. The pharaoh's spirit was believed to navigate these watery passages to the afterlife. In Cambodia, the vast reservoirs were not just for irrigation, they were a representation of the cosmic ocean, with the central temple symbolizing the mythical Mount Meru at the center of the universe. The Maya and Aztecs viewed water as sacred, the source of life and a conduit to the underworld. Their pyramid complexes often incorporated cenotes, natural sinkholes that provided water, and also served as portals for ritual and communication with the gods. The engineering was brilliant, but the motivation was spiritual. This global pattern reveals a shared, profound insight that to sustain a civilization, you must first master water. From the drainage systems that protected the pyramids of Caral in Peru to the aqueducts that fed the Mesopotamian ziggurats, these builders understood that controlling water meant controlling their destiny. They harnessed it for agriculture to feed the thousands of workers, channeled it for ceremony to connect with the divine, and engineered against its destructive power to ensure their monuments would stand for eternity. This universal application of advanced hydraulic engineering points to a common foundation of knowledge, a global recognition that the path to the heavens began with a mastery of the Earth's most vital element. The same mathematical constants appear not only in the pyramids' proportions but also in the very rulers used to build them. A royal Egyptian cubit, the standard unit of measure for the Great Pyramid, was divided into 7 palms and 28 digits, a system reflecting lunar cycles. This same unit of measure, or one remarkably similar to it, seems to appear thousands of miles away. The standard measurement used in the construction of Teotihuacan, known as the Hanab, is nearly identical in length to the Egyptian cubit. How could two cultures separated by an impassable ocean develop and utilize a standardized unit of length with such precision? The mystery deepens when we realize these units were not arbitrary. The Egyptian royal cubit, when multiplied by 10 million, gives a value strikingly close to the polar radius of the Earth. The base perimeter of the Great Pyramid, measured in these sacred cubits, equates to exactly half a minute of latitude at the equator. This is not a coincidence. It suggests the builders possessed a sophisticated understanding of our planet's spherical dimensions, encoding this global knowledge into the very fabric of their local monuments. This pattern of deriving measurement from the Earth itself is a global phenomenon. The ancient megalithic yard found in structures across Europe appears to be based on a fraction of the Earth's circumference. The Indus Valley civilization used a unit that aligned with astronomical observations. It seems that across the ancient world, the most advanced cultures arrived at the same profound idea, to base their most important standards of measurement not on a king's foot or a farmer's stride, but on the immutable constants of the planet and the cosmos. They were using the Earth itself as their ultimate reference point. This points to a common scientific framework, a shared recognition that to build in harmony with the universe, one must first learn to measure it correctly. The cubit and the Hanab were more than just units of length. They were keys to a forgotten science of geodetics, a science that allowed isolated cultures to build monuments that still speak the same mathematical language today. This consistent approach to measurement reveals a startling conclusion that these pyramid builders were not just constructing local temples, they were participating in a global project to map the sacred geometry of the world itself. These incredible structures have survived not because of luck, but through brilliant engineering. The Great Pyramid of Giza rests not on sand, but on a massive, leveled limestone bedrock platform, carefully shaped to distribute its immense weight evenly across the stone. This foundational principle, the use of a wide, stable base to prevent sinking and shifting, appears in pyramids across the globe. At Teotihuacan in Mexico, the Pyramid of the Sun was built over a natural cave, which was carefully filled and reinforced to create a solid, load-bearing core. The builders understood that the ground itself had to be prepared, a universal first step in constructing for the ages. Above the foundation, the very shape of the pyramid is its greatest strength. The wide base and sloping sides create a structure that naturally channels gravitational forces downward and outward, making it incredibly stable. This design is remarkably resistant to seismic activity. During an earthquake, the stacked, often slightly loose stone blocks can shift and settle without causing a catastrophic collapse, a phenomenon engineers call dynamic stability. This same principle is seen in the step pyramids of Mesopotamia, where the terrace design allows for flexibility and movement. The internal architecture reveals another layer of shared genius. Inside the Great Pyramid, a series of relieving chambers were built above the king's chamber, not as rooms for use, but as a sophisticated structural system. These chambers, with their peaked granite ceilings, divert the colossal weight of the stone above away from the chamber below, preventing it from being crushed. This solution to the problem of concentrated load is a hallmark of advanced structural thinking. On another continent, the Maya employed a similar concept with their corbelled arches, where each successive stone course projects slightly inward until they meet at the top, effectively distributing weight down the supporting walls. How did cultures facing the same fundamental challenges of gravity and geology arrive at such parallel solutions? The use of internal buttressing, the strategic incorporation of flexible mortar joints, and the precise angling of walls all speak to a deep, practical understanding of physics. They were not just piling rocks, they were calculating forces. The universality of these engineering solutions, from the foundation designs to the load distribution techniques, points to more than coincidence. It suggests a shared, hard-won body of knowledge about how to make stone defy time, a legacy of architectural wisdom that echoes from the deserts of Egypt to the heart of the Mexican jungle. Geometry was never just about measurement for these master builders. It was a sacred language. The pyramid's four-sided base, found in structures from Giza to the Yucatan, was universally understood as a symbol of the earthly realm, its four corners anchoring the cardinal directions and representing the stable, material world. Rising from this square foundation, the four triangular sides converge to a single point, a powerful visual metaphor for the soul's journey from the many to the one, from the physical plane toward the divine unity of the heavens. This was not a coincidence of design, but a deliberate encoding of a shared cosmological belief that the universe itself is structured by geometry. Inside the temples, this symbolic language deepens. Walk through the complex of Teotihuacan and you will find the repeated motif of the spiral, a shape found in whirlpools and galaxies carved into the stone. This same spiral appears in the intricate carvings of Mesopotamian ziggurats, symbolizing the cyclical nature of life, death, and rebirth. In Egypt, the pyramids were often capped with a pyramidion, a small, pointed stone covered in electrum, an alloy of gold and silver, designed to catch the first and last rays of the sun. This brilliant apex was more than decoration. It was a representation of the Benben stone, the primordial mound from which all creation sprang in Egyptian mythology. The mathematical ratios we find embedded in these structures, the golden ratio and the constant pi, were not merely technical achievements. They were seen as divine proportions, the very ratios that the Creator used to shape the cosmos, from the arrangement of petals on a flower to the orbits of the planets. By building these ratios into their most sacred sites, the architects were attempting to harmonize human creation with the fundamental order of the universe. They were constructing portals of understanding where the geometry of the earth mirrored the geometry of the sky. This recurring pattern of sacred shapes and numbers appearing independently across the globe points to a profound possibility. It suggests that these cultures were not just exchanging goods or techniques, but were participating in a silent, global dialogue about the mathematical nature of reality itself, each one discovering and expressing the same eternal truths through the universal language of stone. These ancient structures were not just monuments, they were living buildings designed to breathe with the planet. In the dry, scorching heat of the Egyptian desert, the Great Pyramid incorporated narrow, precisely angled shafts that channeled the cool north winds down into the heart of the king's chamber, creating a natural air conditioning system that maintained a constant, cool temperature year-round. This was not passive construction, it was active climate engineering. Thousands of miles away, in the humid jungles of the Yucatan, the Maya engineered their own response to a different climate. The towering pyramids like El Castillo at Chichen Itza are riddled with ventilation channels and porous construction materials that allowed the stifling jungle air to circulate, preventing moisture buildup that could erode the stone from within. The core challenge was the same, to preserve the integrity of the sacred space against the elements, but the solutions were perfectly tailored to the local environment. This practical wisdom extended to the very materials they chose. Egyptian builders used light-colored limestone and granite to reflect the intense desert sun, while Mesoamerican architects often covered their pyramids in brilliant white stucco or red paint, not just for beauty, but to shield the underlying stone from torrential rain and relentless humidity. In every case, the builders demonstrated a profound understanding of their local climate, viewing it not as an obstacle to overcome, but as a partner in the design process. They learned to harness the wind for cooling and the sun for symbolic alignment, while deflecting the rain and resisting the Earth's tremors. This global pattern of climate-responsive design reveals a shared, practical genius. It was not enough to build for the gods or the afterlife. They built for the real world, creating sustainable architecture that could endure for millennia by working in harmony with the forces of nature. The pyramid was a universal shape, but its intelligence was local, a testament to a global yet adaptable science of survival written in stone. Modern astronomers are turning back the clock with powerful software, recreating the night skies as they appeared thousands of years ago. When they input the exact coordinates and orientation of the Great Pyramid, they find its narrow air shafts were not just for ventilation, but were precisely targeted at specific stars central to Egyptian afterlife beliefs, like the pole star of that era. This digital time travel reveals a pattern repeated across continents. At the massive complex of Angkor Wat, researchers have demonstrated that the entire temple is an architectural model of the Draco constellation, as it would have appeared at dawn on the spring equinox in the year 10,050. The correlation is stunningly exact. These were not vague symbolic gestures, but precise astronomical instruments built in stone. The methods for observation were as universal as the goals. In Egypt, long, enclosed corridors within temples acted as sighting tubes, framing the rising of Sirius, the star that heralded the annual Nile flood. On the plains of Mesopotamia, the towering ziggurats served as high platforms for priests to track the movements of Venus against the backdrop of fixed stars. In the Americas, the Caracol Observatory at Chichen Itza features narrow, slitted windows that perfectly frame the extremes of Venus's path across the sky. The architectural solutions differ, yet the underlying principle is identical: to create a fixed, unmovable reference point from which to measure the dance of the heavens. This shared technology transformed these pyramids into the world's most durable calendars. The Pyramid of Kukulkan, with its serpent shadow, marked the equinoxes for planting. The placement of stones at Stonehenge, though not a pyramid, shares this same calendrical purpose, capturing the solstice sun. In Egypt, the alignment of the Giza complex allowed priests to predict the annual flood with agricultural precision. How could cultures with no apparent contact develop such a consistent and advanced application of astronomy? The evidence points toward a global scientific tradition, a collective human endeavor to understand time itself by mapping it onto the only truly constant feature of their world, the imperishable night sky. This shared quest to build clocks from stone and stars suggests a deep, fundamental connection in how early civilizations sought to find their place in the cosmos. The sheer scale of these monuments presents a human puzzle as grand as the stones themselves. How did ancient societies, without modern machinery or communication, coordinate the labor of thousands to achieve a single monumental goal? The archaeological record reveals a stunningly similar answer across the globe. In the shadow of the Great Pyramid, excavators uncovered an entire workers' village, a planned community with barracks, bakeries capable of producing thousands of loaves daily, and facilities for processing vast quantities of fish. This was not a slave camp, but a structured, almost corporate settlement providing for a rotating, skilled workforce. An identical pattern emerges halfway across the world. At the base of the Pyramid of the Sun in Teotihuacan, archaeologists found precisely arranged residential compounds, each likely housing a distinct community or guild of laborers who contributed their specialized skills to the grand project. The organization was meticulous. In Egypt, work crews were divided into teams with names like the Friends of Khufu, a detail that speaks to a sense of shared purpose and identity. These teams competed to haul stones faster, their progress recorded in graffiti left within the pyramid itself. Similarly, in the Andes, the construction of massive platform mounds required a system of labor tribute known as mitta, where communities fulfilled their civic duty by contributing a set number of workers for a defined period. This was not brute coercion, but a sophisticated form of social contract. The logistical planning for feeding these armies of workers was another universal challenge met with brilliant parallel solutions. The ancient Egyptians established state-run agricultural estates and granaries along the Nile, creating a surplus that could be transported to the remote desert site. In Mesoamerica, the Maya developed complex raised field agriculture and managed forest gardens to sustainably produce the immense amounts of maize, beans, and other staples needed to sustain the builders of cities like Tikal. The scheduling of work was also tied to the same celestial clock. Construction would have peaked during the dry season or after the harvest, when the agricultural workforce was freed from the fields and could be mobilized for national projects. This shared approach to large-scale social organization with planned housing, state-sponsored food supply, and seasonal labor scheduling points to a common understanding of how to harness human potential. It reveals that the true foundation of every pyramid was not just stone, but a highly advanced and universally applied knowledge of how to unite a society in a common, transcendent purpose. Inside these silent monuments, the ghost of the artisan's hand remains. To carve a pyramid from the living earth required more than grand designs. It demanded a mastery of the smallest details, achieved with tools of surprising sophistication. Deep within the granite quarries of Aswan, you can still see the evidence, perfectly cylindrical core holes drilled into solid stone. Modern engineers have determined that to achieve such clean, deep bores in granite, the ancient Egyptians must have used tubular drills, likely made of copper with a continuous feed of an abrasive slurry, perhaps ground quartz sand. The pressure and rotational speed required suggest these were not simple hand-powered tools, but part of a larger, coordinated technology that could cut through the hardest stone like a modern diamond-tipped bit. This same precision appears across the ocean. At the Olmec sites of ancient Mexico, massive basalt heads were carved with intricate detail using tools made of even harder stone like jade and obsidian. The Maya, too, employed obsidian blades sharper than modern surgical steel to achieve the fine, intricate carvings that adorn their temple walls. They understood that to shape their world, they first had to master the art of the edge. The evolution of these tools tells a story of shared problem-solving. In Egypt, over centuries, we see a progression from stone pounders to copper chisels, and eventually to the use of bronze, each new material allowing for finer work and greater scale. In the Andes, the stonemasons of the Inca civilization developed bronze alloys and perfected a technique of pounding stones together with harder rock pounders to create the famous, seamless joints of sites like Sacsayhuaman. While the specific materials differed, the underlying technical approach was remarkably similar, a relentless drive to find the right tool for the material at hand. This points to a universal workshop principle, a shared logic of craftsmanship, the knowledge of how to temper copper for durability, how to mix the perfect abrasive paste, or how to fashion a resilient hammerstone was as valuable as the architectural plans themselves. This was not random experimentation. It was a cumulative science of materials processing, where successful techniques became treasured secrets, passed down through generations of artisans. The global similarity in these advanced methods suggests that the true connection between pyramid building cultures may not have been a shared blueprint, but a shared, hard-won wisdom about how to converse with stone. Even the myths surrounding these structures speak a common language. The Egyptian pyramid was a machine of resurrection, a vehicle designed to launch the soul of the pharaoh from the earthly realm to join the eternal cycle of the stars. This was not a final rest, but a triumphant rebirth. The entire structure, with its narrow ascending corridors, was a physical representation of the primordial mound, the first land to emerge from the waters of chaos at the moment of creation. The pharaoh's spirit would climb this sacred mountain to achieve immortality. This powerful narrative of ascent echoes across the Atlantic. The Maya viewed their pyramids as symbolic mountains, portals to the other world. The name for their towering temples was Witz, the Mayan word for mountain. Their kings would perform elaborate rituals atop these structures, piercing their own tongues or ears in acts of sacred offering, their blood believed to nourish the gods and sustain the cosmic order. In these moments, the ruler became a conduit between the human world and the divine, his physical ascent mirroring a spiritual one. The parallels extend to creation stories themselves. In Mesopotamia, the ziggurat was the architectural embodiment of the cosmic mountain that connected heaven and earth, a ladder upon which the gods could descend and priests could ascend. Its name, Etemenanke, translates to the house of the foundation of heaven and earth. In the Andes, the Incas told of their ancestors emerging from the sacred caves of Pacaratambo, and their pyramidal platforms, called ushnas, were considered the navel of the world, the central point from which the empire and the cosmos itself were ordered. It is as if every culture, in its isolation, was building a different version of the same metaphysical map. The shared ritual practices are equally telling. The ball courts found at the base of Mesoamerican pyramids were not just for sport, they were stages for a sacred drama, a reenactment of the myth of the hero twins and their journey through the underworld, with the outcome directly influencing the sun's journey across the sky. In Egypt, the Hebsed festival involved the pharaoh running a ritual course around boundary markers, a ceremony of renewal that reaffirmed his power and the stability of the universe. Both were public, ceremonial performances that used the pyramid as a backdrop to enact and reinforce the fundamental stories of their culture. This global recurrence of ascent, creation, and renewal points to something profound. It suggests that these civilizations were not just trading ideas about how to build, but were independently arriving at the same conclusions about the nature of existence. They all perceived a universe divided into layered realms, and they all built the same type of structure, a man-made mountain, to bridge the divide. The pyramid was their collective answer to humanity's oldest questions, a stone prayer for connection with the infinite. These silent stone giants were not merely monuments to the gods, but practical tools for survival. A pyramid's shadow, cast by the rising or setting sun, could become a giant hand on a colossal clock, its tip touching specific markers on the ground to signal the arrival of the rains or the time to sow seeds. In the Nile Valley, the Great Pyramid's precise cardinal alignment meant its sides faced the solstice sun, and the changing length of its shadow throughout the year provided a reliable, large-scale calendar. The annual inundation of the Nile was the lifeblood of Egypt, and predicting its arrival was a matter of civilizational importance. The pyramid's alignments helped priest astronomers track the heliacal rising of Sirius, the star whose reappearance in the dawn sky heralded the coming flood, giving farmers the critical warning needed to prepare their fields. This integration of celestial observation, architecture, and agriculture was a global strategy. Far across the world, in the Mexican highlands, the Pyramid of the Sun at Teotihuacan is aligned so that its western facade faces directly toward the setting sun on the day it passes the zenith, a day that divides the solar year in half and marked a pivotal point in the Mesoamerican agricultural cycle. The entire city, with its precise grid, functioned as a massive celestial calendar, its streets and structures designed to frame solar and stellar events that dictated when to clear the land, when to plant maize, and when to expect the vital summer rain. The very survival of these dense urban populations depended on this stone-encoded knowledge. The spiritual and the practical were seamlessly woven together. A ceremony held at the pyramid to honor a sun god was simultaneously an act of setting the agricultural timetable for the entire community. The pyramid was the central processing unit of the ancient world, a computer built from stone and shadow that harmonized human activity with the immutable rhythms of the earth and sky. This shared focus reveals a universal truth for these early civilizations, that their greatest architectural achievements were fundamentally dedicated to ensuring the most basic human need, a stable and predictable food supply for their people. A single piece of obsidian can tell a story of an epic journey. Deep within the foundations of an Egyptian pyramid, archaeologists have found artifacts made from this volcanic glass, a material whose chemical signature traces it back to a specific quarry in the distant mountains of Anatolia. This was not a local stone. Its presence suggests a network of exchange so vast that it connected the Nile Valley to the heart of Asia Minor. Similar traces of distant trade appear in the Americas, where the Maya prized jade from a single source in the Motagua River Valley of Guatemala, transporting it over hundreds of miles to be placed in sacred caches beneath their towering temples. The movement of these precious materials reveals a hidden map of ancient commerce, a web of routes that carried more than just goods. Along these pathways traveled something far more valuable, the shared knowledge of mathematics, astronomy, and engineering that appears in pyramids worldwide. The very locations of these monumental sites seem to confirm this connection. Look at a map of the ancient world, and you will see a striking pattern. The pyramid complexes of Giza in Egypt are strategically positioned near the terminus of major overland routes from the Levant and the maritime networks of the Mediterranean. In the Americas, the great city of Teotihuacan in Mexico sits at the center of a natural basin that was a hub for the trade of obsidian, a material as vital to their economy as oil is to ours. Farther south, the pyramids of Caral in Peru are located in a river valley that provided access to both coastal and highland trade routes. These were not isolated sanctuaries, but central nodes in a global network of information exchange. The builders were positioned at the crossroads of the world, where travelers, scholars, and artisans from different cultures would have met and exchanged ideas. Could a master architect from Mesopotamia have shared the principles of load-bearing arches with a builder from the Indus Valley? Might a navigator from Southeast Asia have carried stories of celestial alignments used in Chinese pyramids to the shores of Central America? The distribution of pyramid sites along these potential knowledge highways offers a compelling clue. It suggests a world far more interconnected than we once believed, where scientific discoveries did not have to be independently reinvented on every continent, but could be carried on the same currents of commerce that moved obsidian, jade, and spices across the globe. This is not to diminish the genius of these cultures, but to place them within a larger, collaborative human story. The silent stones of the pyramid may be the final evidence of a lost world of conversation, where the blueprint for reaching the heavens was a secret traded along ancient roads and sailed across uncharted seas. These numerical codes are written into the very stones, a silent language waiting to be deciphered. Look beyond the grand shape of the Great Pyramid to the numbers that define it. The ratio of its base perimeter to its original height is not a random figure. It is a close approximation of 2 pi. This means the pyramid's builders intentionally incorporated the ratio of a circle's circumference to its diameter into a square-based structure, a profound fusion of circular and linear geometry. This mathematical constant appears again in the pyramid's interior, where the combined lengths of the Grand Gallery and the King's Chamber also relate to pi. This is not an isolated phenomenon. On the other side of the world, the Pyramid of the Sun at Teotihuacan in Mexico encodes a different, equally significant constant. The ratio of its front platform to its base width reveals the golden ratio, approximately 1.618, a number celebrated for its perfect proportions in art and nature. This same phi ratio is found in the precise layout of the entire city, governing the distances between its major structures. How could builders separated by an ocean and millennia both understand and utilize these irrational numbers, values that cannot be expressed as a simple fraction? The mystery deepens when we examine the dimensions themselves. The Great Pyramid's base side length is 365 cubits, a number mirroring the days in a solar year. Its height multiplied by 43,200, a key precessional number, gives a figure remarkably close to the polar radius of the Earth. In Cambodia, the Temple Mountain of Angkor Wat is designed as a massive model of the Hindu cosmic cycle, its dimensions and bas-relief lengths corresponding to vast astronomical time periods known as yugas. The builders were not just counting, they were encoding the scales of time and space into their architecture. They used their sacred structures as permanent repositories for this advanced computational knowledge, ensuring that the fundamental constants of the universe would be preserved in stone long after their own civilization faded. This shared practice of mathematical encoding points to a common, sophisticated scientific framework, a global understanding that the cosmos itself is built upon a foundation of numbers, and that by building these numbers into their most sacred sites, they were aligning human creation with the divine order of reality. This geological wisdom begins with the unshakable ground beneath our feet. For thousands of years, these colossal structures have stood firm, resisting earthquakes, floods, and the slow, crushing weight of time itself. The secret to their longevity lies not just in their shape, but in the profound understanding their builders had of the earth they built upon. The Great Pyramid of Giza, for instance, was not placed on the shifting sands of the desert. Its builders meticulously leveled a massive outcrop of natural limestone bedrock, carving it flat to within a fraction of an inch to create a perfect, stable platform. This was not a simple task. It was a deliberate geological choice, ensuring the pyramid's immense weight was distributed evenly across a foundation that was essentially part of the continent itself. This same principle echoes in Mesoamerica. The Pyramid of the Sun at Teotihuacan rises from a carefully selected site where builders first excavated down to a stable layer of volcanic rock, then filled and compacted the area to create an artificial but incredibly solid base. They understood that the ground itself had to be prepared, that the earth could not be forced, only cooperated with. Across these cultures, we see a shared process of site assessment. Before a single stone was laid, ancient engineers would have tested the soil, probed for water tables, and studied the local rock formations. In Egypt, this meant avoiding the soft, unstable sediments closer to the Nile floodplain. In the Andes, Incan builders sought out the formidable granite of the mountain ranges. The Maya, constructing in a region prone to sinkholes, learned to identify and build upon stable, limestone bedrock that would not collapse into the hidden waterways below. This was a global, practical science of geology. They learned to read the landscape like a book, understanding that different bedrock types offered different strengths, that soil compaction was vital, and that a foundation was not just the bottom of a structure, but the crucial interface between human ambition and the enduring power of the planet. This consistent, sophisticated approach to site selection and foundational engineering represents a body of practical knowledge so valuable, it would have been worth carrying across continents. It was the essential first chapter in the ancient builder's manual, a universal lesson in how to make a mark on the world that the world itself would not erase. The stones were not the only materials mastered by these ancient engineers. Deep within the pyramid at Abu Sir in Egypt, archaeologists uncovered something extraordinary: metal clamps used to bind the massive core blocks together. These were not simple iron bands, but complex copper alloys, carefully cast to fit into pre-carved grooves in the stone, locking the masonry against seismic shifts. This technique for reinforcing stone against the Earth's tremors appears again thousands of miles away. At the pre-Incan site of Ollantaytambo in Peru, builders used a similar system of bronze clamps to secure colossal slabs of red granite. Even more remarkably, at the Temple of the Sun in Cusco, the clamps were not just poured into place, but were individually forged and shaped before being set. This parallel development of complex metallurgy for architectural stability points to a shared, advanced understanding of material behavior under stress. The selection of stones themselves reveals a deep mineral knowledge that goes far beyond simple durability. The ancient Egyptians chose granite for the interior chambers of the Great Pyramid not only for its strength, but for its high quartz content. Quartz is a piezoelectric material, meaning it generates a small electrical charge when under pressure. Encased by millions of tons of limestone, the granite chamber walls would have been under constant, immense stress, potentially turning the entire space into a subtle energy field. This was not a random choice. In Mesoamerica, the Maya selected specific volcanic stones like andesite for their temples, prized for its interlocking crystal structure that made it exceptionally resistant to the region's humid, erosive climate. They were not just picking rocks, they were analyzing the very chemistry of the Earth, choosing materials based on their crystalline properties and long-term performance. This shared knowledge extended to the processing of these materials. The Egyptians developed a method for drilling granite using tubular copper drills fed with a slurry of abrasive corundum, one of the hardest substances on Earth. This was an early form of precision machining. In the Andes, stonemasons achieved a similar feat, using water and sand as an abrasive with bronze tools to polish granite to a mirror-like finish, a technique that required an intimate understanding of mineral hardness scales. The creation of synthetic materials further demonstrates this global chemical intelligence. The geopolymer theory suggests that some pyramid stones were not quarried, but cast in place using a reacted limestone concrete, a technology that would require precise knowledge of alkaline chemistry. In China, the mortar used in some ancient structures contains organic compounds that have self-healing properties, a sophistication we are only now replicating. The global consistency in this material science is staggering. From the copper alloy recipes of Egypt to the bronze casting of the Andes, and from the geopolymer potential in Giza to the advanced mortars of China, these cultures were all operating with a similar high level of geochemical understanding. They knew which rocks could hold a charge, which metals could resist shear forces, and how to mix Earth's minerals to create bonds that would last for millennia. This points to more than independent discovery. It suggests a fundamental, shared investigation into the properties of the planet itself. They were not merely building with stone, they were conducting a global conversation with the very elements of the Earth, a dialogue written in metal and mineral that we are only just beginning to translate. The same precise geometry that aligned pyramids with the stars may have also guided ancient ships across vast, uncharted oceans. If these structures were simply tombs or temples, why were so many positioned with such exacting geographical awareness, often on prominent coastlines or at the mouths of major rivers? The Great Pyramid of Giza, for example, sits at the intersection of the longest land meridian and the longest land parallel, a global crossroads that seems less like a local choice and more like the calculated center of a known world. This placement implies a cartographic understanding that viewed the entire Earth as a single, measurable sphere. Such knowledge would have been the ultimate treasure for any civilization with seafaring ambitions. Could these monuments have served a dual purpose, acting as both spiritual centers and colossal navigation beacons for a global network of maritime explorers? Imagine a sailor navigating the featureless Mediterranean Sea, a pyramid constructed on a high coastal point, its gleaming white limestone casing stones reflecting the sun would have been visible for miles. Its distinctive silhouette against the sky would have provided an unmistakable landmark, a fixed point of reference in a world without compasses or charts. This concept repeats across the globe. The pyramids of the Moche culture in Peru were built overlooking the Pacific, their massive forms acting as guides for coastal travel. In Mesopotamia, ziggurats rose from the flat plains near the Persian Gulf, their towering heights serving as the first and last sight of land for ships embarking on or returning from long voyages. The alignment of these structures often points not just to celestial bodies, but to other distant pyramid sites, creating a chain of waypoints across the landscape. This system of landmarks would have functioned as a prehistoric global positioning system, a network of stone sentinels guiding knowledgeable travelers from one continent to another. The builders were not just mapping the heavens, they were creating a permanent, physical map of the Earth itself, written in mountains of stone for those who could read its language. This suggests a world where geographical knowledge was a sacred science, carefully encoded into the most enduring structures a civilization could build. The silent pyramids standing on our shores may be the last remnants of a forgotten age of exploration, when the oceans were not barriers, but highways connecting a planet already known to its earliest inhabitants. Step into the king's chamber of the Great Pyramid and hum a single, low note. You may feel the very air around you begin to pulse, the sound waves amplifying as they bounce between the polished granite walls, creating a resonance that seems to fill the space with invisible energy. This is not an echo, it is a carefully engineered sonic environment. The chamber's dimensions, a perfect 2-to-1 ratio of length to height, are not arbitrary. They correspond to a fundamental musical interval, the octave, the most consonant and stable relationship in harmonic science. This deliberate design, turning an entire room into a giant musical instrument, is a phenomenon that spans the globe. In the subterranean chambers of Mayan pyramids, like the one at Palenque, the stone construction creates a unique acoustic signature where certain frequencies are enhanced, while others are absorbed, producing a deadening effect that can make a whisper sound like it is coming from inside your own head. The builders were not just working with stone, they were composing with space itself, using the mathematical ratios of music to shape the sensory experience of their sacred sites. These ratios, the same ones that govern the harmonic series of a plucked string, are found encoded in the floor plans and elevations of pyramids from Mesopotamia to Peru. The golden ratio, so prevalent in their geometry, also defines the perfect fifth, another powerfully resonant musical interval. This shared architectural language of vibration suggests a profound cross-cultural insight that the universe itself has a fundamental frequency, and by building structures that harmonized with it, they could create portals of heightened spiritual awareness. The consistent application of these principles points to a universal discovery, an ancient science of sound that understood how specific resonant frequencies could alter human consciousness, calm the mind, or induce a state of receptivity. It was a technology of transcendence, built not with circuits and wires, but with the eternal, vibrational laws of physics, whispered from one culture to the next in the silent language of mathematics and stone. Modern researchers are placing sensitive instruments beneath scale model pyramids, measuring unexpected energy concentrations that seem to defy conventional physics. These contemporary experiments echo a belief held across the ancient world that the pyramid shape itself could influence health and consciousness. Historical records from Egypt describe special chambers within temple complexes where individuals sought restoration, their design intended to harness beneficial energies from the earth and sky. Across the Atlantic, Mesoamerican shamans performed rituals in the secluded chambers atop their pyramids, spaces believed to be conduits for healing forces from the spiritual realm. This was not superstition, but a sophisticated application of environmental medicine. The architectural features thought to enhance well-being are remarkably consistent. The precise proportions of the king's chamber in the Great Pyramid, for instance, create a specific resonant cavity. Some researchers propose that these carefully calculated dimensions could generate a standing wave of infrasound, a low-frequency vibration below the range of human hearing that has been studied for its potential to reduce stress and promote tissue regeneration. Similarly, the narrow, precisely angled shafts found in many pyramids may have functioned as more than air vents. They could have been designed to channel and concentrate subtle geomagnetic and telluric currents, the natural energy flows of the planet itself. Imagine a space where the very architecture works in concert with the human body's own energy field. The use of specific stones amplifies this effect. Granite, with its high quartz content, was chosen for the most sacred chambers. When compressed under millions of tons of stone, these quartz crystals can generate a mild piezoelectric field, potentially creating an environment that influences cellular function. This shared architectural focus on creating restorative environments reveals a profound, universal principle. These ancient cultures, in their isolation, all arrived at the same conclusion, that the places we inhabit are not passive shelters, but active participants in our well-being. They were building more than monuments, they were constructing therapeutic instruments of stone, encoding a lost science of how our health is intertwined with the energy of the earth and the geometry of our spaces. These silent stone libraries were built with a single, urgent purpose: to preserve humanity's greatest discoveries against the relentless erosion of time. The pyramid was far more than a tomb or a temple. It was a sophisticated time capsule, its very stones holding the core scientific and spiritual knowledge of an entire civilization. The builders knew that empires fall, that languages are forgotten, and that scrolls can burn, so they chose the most durable medium available: architecture itself. to encode their understanding of the universe for generations they would never meet. In Egypt, this took the form of mathematical constants deliberately embedded in the pyramid's proportions. The relationship of its height to its perimeter, a clear expression of pi, was not an architectural flourish. It was a permanent record of an advanced geometric principle, a lesson in stone that would remain legible long after the civilization that created it had turned to dust. Across the ocean, the Maya achieved the same goal through celestial choreography. The serpent of light descending the pyramid of Kukulkan at the equinox was a complex astronomical message, a working model of the solar calendar that would continue to function and communicate its meaning century after century, independent of any spoken language. This shared methodology reveals a profound and sobering global insight, a recognition of civilization's inherent fragility. These cultures, separated by continents, all arrived at the same solution: to convert their most vital knowledge into a format that could withstand wars, natural disasters, and the simple forgetfulness of humanity. They embedded information in the angles of shafts pointing to specific stars, in the precise cardinal alignment of foundations that served as a permanent compass rose, and in the harmonic ratios of chambers designed to resonate with the fundamental frequencies of the Earth. The very act of building on such a colossal scale was a declaration, a statement that their understanding of mathematics, astronomy, and engineering was too valuable to be left to perishable materials. They were speaking directly to the future, using a universal language of number, alignment, and form that they trusted would one day be understood again. This consistent, global commitment to preserving the pillars of knowledge suggests a shared memory of loss, a collective understanding that the light of discovery is fragile and must be encased in stone to survive the long, dark nights of history. This central debate divides scholars and enthusiasts alike. Did a single, lost source of wisdom travel the globe, or did humanity's genius simply converge on the same perfect form again and again? The case for cultural diffusion rests on a web of startling parallels. We find similar phonetic sounds in the names for the sun across distant languages, and creation myths that speak of bearded wisdom bringers arriving by sea. The technology itself forms a compelling thread: the specific method of drilling granite with tubular drills and abrasives, or the complex lost wax casting used for metal clamps in Egypt and the Andes. These are not simple ideas like the wheel or fire. They are sophisticated, multi-step processes that seem too specific to be endlessly reinvented. Proponents of this view point to potential maritime routes, ancient maps that hint at transoceanic travel, and the strategic placement of pyramid sites along coastlines as if marking the ports of a forgotten global network. They argue that these intricate similarities are the scattered pieces of a single, ancient instruction manual for civilization. Yet the argument for independent invention is equally powerful. Human minds, when faced with the same fundamental challenges, often arrive at similar solutions. The pyramid is, after all, the most stable way to stack stone towards the sky. Every culture that mastered agriculture faced the need for a calendar, and looking to the stars was the most logical answer. The development of advanced mathematics could have emerged separately in each society as a natural progression from counting and trade. The archaeological record, for now, shows no solid evidence of direct contact, no Egyptian artifacts in pre-Columbian Mexico, no Mayan pottery in ancient Egypt. The timelines are also staggeringly vast, with thousands of years and oceans separating the rise of these pyramid-building cultures. This perspective suggests that the pyramid is not a relic of a single parent culture, but a universal milestone in human development, a shape that emerges naturally when a society reaches a certain level of technological and spiritual sophistication. It represents our collective human response to the fundamental desires to reach for the heavens, to understand the cosmos, and to create something that will outlast us all. As we weigh the linguistic hints against the silence of the archaeological record, and the technological echoes against the immense gaps of time and space, we are left with a mystery that defines our past. The answer may not be a simple choice between one or the other, but a more complex tapestry where sparks of independent genius were fanned by whispers of a knowledge carried on ancient currents. The stones have spoken a universal language of numbers and stars, a chorus of knowledge that once connected the ancient world, from the precise value of pi in the Great Pyramid to the golden ratio gracing the temples of the Maya, from the celestial maps of Giza to the solar calendars of Teotihuacan. We are faced with a tapestry of evidence too consistent to be mere chance. These shared scientific principles, encoded in stone across continents, point toward a profound interconnectedness that challenges the very timelines of our history books. It suggests our ancestors possessed a sophisticated understanding of the planet and the cosmos, and that this knowledge was exchanged on a scale we are only just beginning to comprehend. While many mysteries remain, the pattern is undeniable, a silent testament to a forgotten chapter of human collaboration and genius. The true significance of these global parallels may extend far beyond what we currently understand, hinting at the depth of human capability and the potential for lost sciences we have yet to rediscover. This journey through the echoes of ancient engineering is far from over. I invite you to continue exploring these fascinating connections. Share in the comments which parallel you found most compelling, the mathematical codes, the astronomical alignments, or the shared myths of Ascent, and let us keep the conversation